Hi, folks. Our first video segment for today, for this week, isn't actually from chapter 2. It's a review of what happened when I tried to use the oscilloscope for experiments 1 and 2. So I've got our binary counter, 0 through 15, wired back up, and you can see the LEDs are playing along, doing their, counting from 0 through 15 and then back to 0 again. You can see that I've got a oscilloscope lead here connected with this white cable to the output QA. It's the same, this white cable is the same one that was going to lamp 0 the other day. And if I adjust my phone a little bit, you can also see this green wire here attached to another oscilloscope lead. And I'm going to leave this one alone. It's right now and will be for the rest of the video. It'll be showing us the same output or input, I guess. What is being fed on pin 14 to this chip from the function generator down here. So this is the sequence of ons and offs like we would get by pressing the pulse button over and over again. And we tried the other day to use the oscilloscope to sort of observe this sequence of asserted and unasserted signals. And the oscilloscope was just giving us a nice sinusoidal oscillation, which didn't make a whole lot of sense to me at the time. I feel like it's an issue that I should have been able to troubleshoot at the time, but I had my head in digital electronics and I wasn't thinking about analog electronics and circuits with resistance and capacitance and alternating current. I was thinking about signal values and the fact that something was going wrong. It didn't even occur to me to think about the power circuit coming from the wall. And I'll show you what I mean. I'll turn the oscilloscope on for a second. Right now, I'll turn the breadboard back off. So we should be seeing nothing from the scope because nothing is happening on the breadboard. This is not an active chip. No lights are flashing. We should see 0 signals. And if we let the scope finish its on process any minute now, and we do in fact see a flat horizontal line across the screen. Nothing happening. If we turn on let me make this a little bit bigger so you can see what's going on, and I'm going to stop the screen so it stops refreshing. And there or so. And you can see patterns alternating of the yellow channel, which is channel 1, highs and lows, and then highs and lows again, and another pattern within that, and that is the response from QA. We expect QA to change its value, to change whether its signal is asserted or unasserted at half the speed of the signal from the generator. And the reason for that is we have to turn it, the signal from the generator turns it on, QA, and then we need another signal from the generator to turn it off. So every time the generator signals, there is a change in the state of QA. So we need 2 generator signals to take us through a single transition for QA. And that's why we expect it to change its value half as fast. So we can see, and I'm gonna move my phone so you can see this screen a little bit better. You can see the yellow channel response, and it has a high value and then a low value. And when the yellow channel, that is channel 1, the frequency generator, makes its falling transition from high to low, that's when also, sorry for the, need a GoPro or something here. That's when channel 2 also makes its transition. The next time we get a falling transition from channel 1, the function generator, that's when channel 2 makes its next transition. It's not always a falling transition from channel 2, but whenever channel 1 falls, that's the signal that tells channel 2 to change. And this is the response that we were supposed to see. Now, why were we seeing what we did see the other day? I turned off the breadboard, and I think you can see that the lines went back to flat, no activity. I'm going to unplug the breadboard for a second. I'm going to try to unplug the breadboard for a second. I've got a nest of cords back here. This is the right one. All right, unplugged the breadboard, and note the oscilloscope response has already changed. Check it out. We've got this jaggedy kind of nonsense going on. I'm going to turn off channel 2 so it's easier to see. But channel 1 now has this kind of shape to it. And if I zoom in a little bit, there's this oscillatory nonsense going on. Not really clear where that's coming from. If I plug in the breadboard using a different outlet, so instead of that one over there, I'm using this one here, and I need an adapter because this kind of plug it's only a 2-prong plug. So this is some, rinky-dink adapter I'm using, and it's only 2 plugs. It won't accept the 3-pin plugs. So I've got this adapter that goes from 3-prong down to only 2-prong, and the ground connection is just like hanging out loose over here. So if we plug that in, now I haven't done anything to the scope. All I did is plug in the breadboard. It's not on. All I did was plug it in. And now the oscillation on channel 1 is off the screen. Like it's off the chart. I have to zoom out to even see it. And this is that oscillatory thing that we were seeing in class. Note the indication. If I set the trigger, which has to do with updating or not updating the display, I'm going to set it to channel 1, and it's going to do some calculations for us and tell us how channel 1 is changing. We'll go back to this menu. Okay. It says triggered because the little yellow trigger here lives in the scope of the signal from channel 1. So it's just going to pause the screen and not update it. If I move the trigger away, then we get a real-time update. But if we put the trigger into the, I guess the range of the signal, it pauses the display and just shows us one picture. But it shows us a really nice oscillatory picture with a frequency of 60 hertz. Now, if you have had some electronics, you know that electrical power is delivered to houses and, rooms, to buildings by the power grid at an AC, alternating current frequency, of 60 hertz. All of our outlets, at least the ones that are for normal, everyday appliances, a dryer, a clothes dryer is often a different kind of outlet, a commercial outlet, and that's 220 volts. But most of our normal outlets are 120 volts, 60 hertz alternating current. That 60 hertz alternating signal, because this plug isn't making the ground connection that it ought to be, that 60 hertz signal is coming through the electronics of the breadboard, whether it's on or not. We turn it on, and whatever we try to do, whatever logical thing we try to do, yeah, it happens, but it's almost like it can't, it's like noise happening on top of that, like really, really strong, really fundamental 60 hertz signal. Check it out. If we turn off the trigger, you can actually see some variations in, and you can actually see, so like it's triggering sometimes because the amplitude of the signal is varying a little bit. You see that spike right there? Those spikes happen when whatever signal is coming from the function generator overlaps just right with the 60 hertz back, like the base 60 hertz of the signal. And it's adding together just enough to reach the trigger threshold, and it'll pause the display for just a second. So why couldn't we see anything the other day? It's because I had the breadboard plugged into the wrong outlet. So turn the breadboard off. Goodness. Unplug that breadboard. Plug it back into a normal 3-prong outlet over here on this power strip. Notice that the signal on channel 1 immediately quiets down because of that ground connection that we're making is now grounded and very, very quiet. And now when we turn on, we can see a pattern of alternating highs and lows, alternating asserted and unasserted. Okay, so let me get this display to a point where we can see what's going on. And I'll probably use my phone to show you this because I want to get up close and detailed with it. Let's see here. This is pretty good. Let's turn on channel 2. All right. So you can see that the breadboard is still doing its thing. We've still got our output that's counting binary for us. And let's see what this looks like. We saw this already, but I just wanted to point it out. we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 high points in channel 1. And every time we get a falling transition in channel 1, we see a transition in channel 2. So this blue channel is the output for QA. We can see that pattern continue. If I instead make the wire that is attached to my measurement lead, if I attach it not to QA, but to QB, now QB was pin 9. That's the yellow wire. So if we make that connection, you can see that the yellow channel is unchanged, but that the blue channel now takes twice as long to make its change. It changes once for every 2 falling clock transitions. So it's, again, half as fast as channel QA. Pause that for a second. There are, if we transition down so that the channel QB becomes asserted, we stay asserted for 1 falling transition, and then on the next falling transition, that's when we change. So this channel QB output is twice as slow. I mean, it's happening only half as fast as QA's transitions were happening. If we change from channel QB to if we change the location of the oscilloscope lead, if we look at output QC, now we wait for transitions. And the fact that this sort of display is shifting to the right is just a feature of the refresh rate of the display and the actual frequency that we're working with. And last but not least, if we take a look at QD, you can see that our channel 2 preserves its value for 8 transitions of the function generator, and then makes its transition and stays there for 8 more transitions of the function generator. I'm going to pause the screen now. Sorry. I wanted to get a full. As you can see, 1 falling transition of the function generator here, and then that kept us 0. This blank spot is the refresh sort of sweep of the scanning oscilloscope method. But all the way through, it looks like it would be 1 and another 1. So that's 1, 2, 3, 4, 5, 6. Maybe there are 3 there. Well, hold on. Let me take a look. Let's see if we can find. There we go. So here's a falling transition. 1, 2, 3, 4, 5, 6, 7. And on the 8th falling transition, that's when our signal QD makes its next transition. This is the kind of timing diagram that we were expecting when we were working on the lab the other day. So that's what it ought to have looked like, and you can refer back to that anytime you like, now that we have it recorded. And now we know why, and it's something to keep in mind as we go through our next few chapters. Cool. All right. Moving on to new content from chapter 2.